Hi, I'm Dr. Nigel. I'm going to talk about Einstein's theory of special relativity, the easy bits. Yes, there are easy bits. The problem is that when you go to a course on Einstein's theory of special relativity at university or in college, they want to get you to the exam at the end of the year as quickly as possible. And that usually has quite a lot of maths in it. And so the easy bits, the exclamation, these are left either to you to find out yourself, or they go through them very quickly in a few minutes in the first lecture. Whereas the actual easy bits are the most important and they're the easiest. When I get to the hard bits, I'm going to stop. So no panic. So what do we actually need? And where are we coming from? The idea behind Einstein's theory is really to answer the question of how things move in space and time. And it turns out that in order to at least think about or calculate or do anything about how things move in space and time, we need two things. The first thing we need is to be able to identify unique locations. And the second thing that we have to do is we have to be able to define the separation between these unique locations. Now, you might be wondering, well, unique locations in space and time, unique locations, aren't they just points? Didn't we learn about that in primary school? What is a point? Well, the answer is yes to both. It's that simple. We have to define points in space and time. But in order to do that, we need a proper system, and the first person to come up with a proper system was a French mathematician called René Descartes. He did this in 1637. Now, René Descartes was an interesting mathematician. He was the only mathematician I can recall that carried a sword around with him most of the time, especially when he was younger. He was a soldier, an officer. He came from a reasonably wealthy family, not particularly super rich, but wealthy. He dressed very well, and he travelled around Europe, particularly in France and in Holland, and he worked for various people. You've got to think of these times in the 17th century in Europe much as you might think about the Wild West in America in the 19th century. You had a lot of people going around with guns and guns for hire, and it was a bit lawless. Well, it was a sort of similar to Europe in the 17th century, except instead of carrying around guns, people carried around swords. There were guns, but they generally carried swords around. There's a lovely story of Descartes. He was in an inn and in Holland, and there were two cutthroats, rather horrible looking men at the bar talking, and one of them said to the other in Dutch, let's take his money when he goes out, the rich Frenchman sitting over there. Well, Descartes heard what they said, and being able to speak fluent Dutch, he went over to where they were. He drew out his sword and held it to the throat of one of the men and said, "If you're going to rob me, I'm going to cut your throat." Well, after that, the men were very apologetic. He was a fine swordsman, Descartes, and they said there'd been a misunderstanding and they didn't really mean that, and that shows you the sort of person that he was. Didn't stand for any nonsense. Well, he was in an inn one night, and inns in those days were sort of the equivalent of hotels today. They didn't really have hotels in those days. And they weren't furnished very much. And even an inn that was quite good would have all the walls whitewashed. There wouldn't be any nice finery or drapes or wallpaper or anything like that. And he was in bed one night looking up at the ceiling, which had just been whitewashed. And on the ceiling was a spider. Now, I know some of you might be a bit scared of spiders, so I've drawn over here on the right-hand side a representation of Descartes' ceiling. And there's a spider sitting there in the corner. Because some of you might be scared of spiders, I've tried to put a smiley face on the object. And what Descartes thought of was the following question: how can I tell somebody in another room exactly where the spider is on my ceiling? So he thought of this idea. The idea he thought of, well, the center of the ceiling, I'll call a point the origin, and then I'll put a line through that east-west, and I'll call that the x-axis. And then at the origin, I'll then put another line at right angles to the x-axis and call that the y-axis. And then all I'll do is I'll drop perpendiculars from the spider to the x-axis and the y-axis, and I'll call those distances x and y. And the x and y coordinate will determine the exact position of the spider on the ceiling. And if I tell someone in the next room with a similar ceiling, my spider's at the point xy, he or she should be able to tell exactly on the ceiling where the spider is. We recognize all this as what we call Cartesian coordinates. And this was in 1637. I'll now move on to separation, and I'll come back to Descartes in a minute. So here's the next guy. This is Pythagoras. You may remember him because of his lovely theorem on triangles. Pythagoras lived around the 6th century, probably about 570 to 495, something like that. And he also came from a fairly wealthy background. And for students at that time, if you were from a reasonably wealthy background, you took a gap year, or maybe you took a gap 2 years, I don't know. And he travelled eastward from Greece and Turkey, and he travelled to India. India was the place to go in those days because they were quite advanced. There was a lot of mathematicians and scientists in India, and he travelled round. And when he came back, he brought back with him this theorem. We now know this theorem as Pythagoras' theorem. Of course, Pythagoras' theorem was known hundreds and hundreds of years before Pythagoras, but he showed a few proofs of this theorem, which I'm not going to bore you with. The theorem says that if you have a right-angled triangle, then if S is the hypotenuse, the longest side, and the other sides we call x and y, then there's a formula. S squared is equal to x squared plus y squared. Now, okay, the Pythagoras' theorem is taught in schools, and I admire the theorem very much. But I'd like to modify the theorem, not modify, add to the theorem. It's not the whole story. You see, I said for a right-angled triangle, S squared is x squared plus y squared. So I'd like to change the wording of the theorem from a to any. And what we have is for any right-angled triangle with the same hypotenuse, S, x squared plus y squared equals s squared. At first sight, it might not seem that there's any difference between that and the first Pythagoras' theorem, which I gave you. The difference is this guy. There isn't a very good picture of him, I'm afraid. His name is Thales. He's about 50 years older than Pythagoras. Pythagoras and Thales met each other when Pythagoras was quite young, a student. Thales died probably when Pythagoras was about 20, but they did meet each other, and he also came from probably a moderately wealthy family, and he also did his gap year or years in India, and he came back with another theorem, which we actually call today Thales' theorem. Thales' theorem says if you have a diameter of a circle S, and I've drawn here half of the circle around the diameter, then if you join up the two ends of the diameter to the circle, the triangle that you get always has 90 degrees as its apex. And you can do this all the way around the circle if you want to. So for all of these triangles, s squared is equal to x squared plus y squared, where x and y are the two other parts of the triangle. In other words, we can change coordinates. You can have x and y, and then s squared equals x squared plus y squared, but you can change coordinates to other coordinates, x dash and y dash, say. And then x dash squared plus y dash squared is still equal to s squared, because all of these triangles have the same hypotenuse. This is an extension of Pythagoras' theorem, which is quite important for our purposes. So the first thing is I have basically gone into 2 dimensions. What about the 3 dimensions? I said we need to identify points in space and time, and space has got 3 dimensions: length, breadth, and height. Here's a little diagram which shows that, and I can also put letters on these lengths. So S here now is the diameter of a sphere rather than a circle, and X, Y, and Z are the 3 coordinates of length, breadth, and height. And it's not too difficult to see that we can actually extend this theorem to 3 dimensions. In other words, if x squared plus y squared is this length AC squared, and then go into the other triangle, AC squared, which is x squared plus y squared, add to it z squared, and then that gives you s squared. So going into 3 dimensions is really easy. You just add another z squared to it, to the formula, but you still got s. And we can still change all these coordinates as we go around the sphere. So we can have x dashed, y dashed, and z dashed as another coordinate system, but the diameter of the sphere is the same, so s is always the same. So s squared is equal to the sum of the squares of the 3 coordinates. Now that's as far as space is concerned. What about time? I haven't mentioned time. Well, the problem with time is twofold. Number one is time is measured in seconds, years, hours, millennia, whatever you like, different to how you measure distance, which is measured in meters, or you could measure it in miles, or parsecs, or anything you like. In equations in physics, if you have a left-hand side and a right-hand side of an equation, they have to have the same units. So we've got here an s squared, which is basically a distance squared. All the other 3 are all distance squared. So if we're going to add a time into here, we need to change the time into a distance. Now there's a way of changing time into distance, and that's due to this guy. This is a Scottish mathematician, and he's called Maxwell. And in 1865, he was interested in a theory of electromagnetism. Let me wind back a little bit and make it really easy. Do you remember when you were young, and some of you might still be young, and you went out with your friends, and if there was a lake or a pond or something like that, young children find it very difficult to resist the temptation to pick up a stone and throw it into the water, particularly to see if you can make it bounce, like this picture here. The thing about bouncing stones off the water is every time the stone hits the water, you get this circular wave motion coming from where the stone hits the water. And you bounce the stone, you get lots of these different waves. The thing that you may or may not notice is that the waves all go out exactly symmetrically in the water as circular waves. And the speed of the waves as they move out from the point of contact doesn't depend on the speed of the stone. In other words, you could drop a stone vertically and you'll get the pattern, or you can shoot the stone from the left to the right as fast as you like. As the stone touches the water, you get the circular pattern. And I think you can realize that the pattern is in the water. It's nothing to do with the stone. The only thing the stone has to do is to touch the water. It's the actual touch that causes the waves to occur, and the waves occur in the water. So they don't depend on the speed of the stone. Maxwell found exactly the same thing in his equations for electromagnetism. He found that he could work out the speed of waves in space, in a vacuum of space, and these waves would travel at a universal constant, the speed of light, which is about 186,000 miles a second. And this speed of light didn't depend on the speed of what was causing the light. So if you have a torch and you switch the torch on, the light comes out at the speed of light. If you have a torch moving at 100 miles an hour and you switch it on, the light still comes out at the speed of light, 186,000 miles a second. It's not dependent on the speed of the torch. And that's what he found. According to this, at the time, people assumed that there must be some sort of medium that the light travels in, even in a vacuum. We now know that that's not the case, but we still know, and Einstein accepted Maxwell's theories, and we have that there's a universal constant, c, the velocity of light. Because it's a universal, it means that if you multiply time by c, you get a distance. You get the distance traveled in the time t by light in a vacuum. And we can use ct as a distance, and we can put that in the equation. There is still, however, one slight problem. If you put ct in the equation as a square, c squared t squared, you can't just simply add it in, because we know and we expect and we assume that time is independent of space. So that's all right with 3 dimensions, x, y, and z. They're all independent of each other. But if you put another dimension in, ct, or ct, c squared, t squared, if you just simply add it in, then the t, or the ct, will be part of the x, y, and z. And that means it won't be independent. So we need t to be independent of x, y, and z. This was solved by an Italian-American physicist called Gianfranco Wick. He didn't solve it until 1954. Now, many of you might say, hold on a second, Einstein's theory of special relativity is 1905. And he didn't work out this little bit that I'm going to tell you until 1954. Doesn't matter. I'm not following chronology here. What I'm following is the easiest way to understand the easy bits of special relativity. And Gianfranco Wick worked it out to make it really easy. He lived in America, and he was obviously of Italian descent as well. And the only thing I know about him is he did suffer in the McCarthy era in America in the 1950s. And he had a lot of difficulties there in his job and so on. The other thing I know about him, he was a keen mountaineer. He liked to climb mountains, which I suppose in a sense is common with many mathematicians and physicists. We all like to climb mountains, although not physical mountains. We like to climb intellectual mountains. He managed to do both. So what did he do? He invented what is known as the Wick rotation. Now, we're used to equations with numbers in them, but there are also equations that have what they call operators in them. Most of our equations have both a mixture of operators and numbers. So 1 plus 1 equals 2. The 1s and the 2 are numbers, and the plus and the equals are operators. Wick had an operator called, I'll call it R, and I put a little hat on it to show that it's an operator, it's not a number. And his Wick rotation is very simple. You've got the number 1 there, which I've represented by an arrow, and his Wick rotation simply rotates this 90 degrees. So the arrow that's pointing up in the diagram is just the one that's down here that's been rotated 90 degrees. And that's the Wick rotation. Now Wick said there's nothing to stop you doing the rotation twice. So R1 gets you to here, and then RR simply means that you're doing it twice. So that gives you 2 Wick rotations. And the beauty of this is that the 2 rotations, you end up with -1. If you start with +1 and you rotate 90 degrees twice, you end up with -1, which gives you the remarkable operator equation, RR is equal to minus. What does this mean? Well, we're used to operator equations. I know you're thinking, operator equations? I've never seen an operator equation before. Well, let me remind you, way back in primary school, when you were very young, the operator equation minus minus equals plus was taught to you. We now know, and we use all the time, whenever you see a minus minus in an equation, you replace it with a plus. That's an operator equation. So Wick's operator equation is when you see RR, you just replace that with a minus. Well, let's do it. So RCT, that's the rotation of the distance travelled in a time t by 90 degrees, and then we do it again by 90 degrees, and that gives us RRCCTT. That's the square of RCT. And that, because of this RR equals minus operator equation, means that we've just simply got a minus, and then we've got c squared t squared. The sum total of all this effort is that our equation that I had before for s squared, the Pythagoras' equation, in 4 dimensions now is x squared plus y squared plus z squared minus c squared t squared. In other words, according to Wick, we can make time independent of x, y, and z by making time, as it were, at right angles to each one of these 3, or what they say in mathematics we say is orthogonal or independent of. And by putting the minus sign in means that time now is independent of space in this equation. So this is just Pythagoras in one more dimension, time, x, y, z, t, but the time has a minus associated with it. Here is our equation. So how did we get here? Just to reiterate, we got here in the following way. First of all, we started with Pythagoras and Thales, and that gave us the different coordinate systems. We can work out s squared, the separation between 2 points in space and time. And we had to have time and space independent. And if we had time and space independent, and we say, okay, Maxwell's theory is correct, that means that the velocity of light, c, is a universal constant, and we can use it up here to change the dimensions of time to space. And then we add 2,500 years, and here we are. We've got this equation. Just to reiterate, here are the rogues gallery. We had Descartes, Pythagoras, Thales, Maxwell, Wick, and Albert Einstein. And you put these things all together, and we've got our equation. S squared equals x squared plus y squared plus z squared minus c squared t squared. Okay, so now let's have a little story, because an equation like this doesn't really mean anything. So let's work out an actual situation. Well, the situation I'm going to work out, which I've very badly drawn here, is me sitting down in a chair with a clock on my lap, and a friend of mine walking away from me with a very similar clock which they're carrying. I have to say that I'm glad that I'm sitting down in the chair and not carrying the clock. It looks quite heavy, even though the person I've tried to draw has got a little bit of a smile on their face. So what's the situation here? Okay, let's have a look. Me sitting down in the chair, I can say my x is 0. I can make that coordinate system whatever I like, so I can center it on me. So x is 0. I'm not interested in y and z. I can put them 0 as well, and I can make my friend walk in the x direction away from me. So that means that s squared for me is equal to just minus c squared t squared. Everything else is 0. Now I go to my friend. Now my friend, I can't assume for the moment that the time on their clock is going to be exactly the same as mine, so I call it TF, the time of the friend, and they're going to measure the distance that they're moving away from me, XF. For me, X is 0, but for my friend, there's a certain X that they're measuring as they're moving away from me, their time, which they're measuring on their clock. So for my friend, S squared is equal to XF squared, that's the X that they're measuring, Y and Z are 0, because they're moving in the X direction, and T is TF for the time they're measuring on their clock. Now these two S's are the same. The whole thing that we've been doing so far is showing that this S is an invariant quantity. It doesn't matter what the coordinate system is. In fact, there's an interesting thing here that Einstein, when he first mooted his theory, wanted to actually call it invariant theory. But I don't know quite why. I think it's the people who published his work in the journal decided that they didn't like invariant theory, or maybe someone persuaded him not to call it invariant theory, so he called it relativity. So we've got minus c squared t squared is equal to xf squared minus c squared tf squared. Well, what we can do is we can divide both of these sides by c squared, and then we can take the square root and we can call xf over tf v. V is the velocity that my friend measures, the distance he or she is moving after a time t that they are measuring. And if you do that, take the square root, you get this formula. Tf is equal to t divided by the square root of this horrible thing, 1 minus v squared over c squared. So here's the formula. Tf equals t over that square root. So what are the consequences of this formula? Well, it turns out that there are quite a few. First of all, moving clocks show different times. Unless v equals 0, tf and t are different to each other. The second thing is V can't be greater than C because, as you know in mathematics, you can't have the square root of a negative quantity that you can measure. Yes, I know you can have complex numbers, but you can't measure complex numbers directly. You can only measure real things when you take out a tape measure. And so V has to be less than C. In other words, nobody can travel faster than the speed of light. The third thing follows from the first. If T, F, and T can be different, for different V's, then Newton is wrong. There's no ifs and buts here. Newton would say time is universal. Everywhere you can measure the same time. There's no difference in time as to how fast you're moving. So Newton is wrong. The fourth consequence is, of course, atomic weapons. The fifth consequence, which is relevant to us particularly, is you get textbooks full of equations. Some of these equations can be really complicated. So this is a good place to stop before things get really, really complicated. And I'd like to just add a little advert here for our website where we produce textbooks on physics and maths. Thank you for watching.